For each of the following graphs, determine whether the graph has an Eulerian trail, an Eulerian circuit, both, or neither, and state why. And if the graph has an Eulerian trail or an Eulerian circuit, show one example. Let's start with the first one. The first one, let's have a look at the conditions for the trail and the circuit. So for the trail, we need the graph to be connected, and for the circuit, we also need the graph to be connected. And if you have a look at this graph, it is indeed connected, so we've already satisfied that condition for both. Now, the second condition for the trail is that it has to have exactly 0 or 2 vertices that have an odd degree. So if we have a look at this one is degree 2, this one is degree 2, this is degree 2, and this is degree 2. So we do have 0 vertices that have an odd degree, so therefore the trail exists in this case. If we look at the circuit, we can see that our graph is connected, and it says vertices all have an even degree, which you can see in our case 2, 2, 2, and 2 are even. So therefore, we have both the trail and the circuit as well. Okay, so in this case it's both, and the reason why is because there are 0 odd vertices. And in part 2, it says if the graph has a Eulerian trail or a circuit, show one example. So in our case over here, I'll just eliminate these markings. So we could have A as our starting point, and then go to C, and then go to B, and then go to D, and then go back to A, and that would be an example, because if you look over here, a Eulerian trail follows every single edge with no repeated edges. So we managed to trace the entire graph just like that without repeating any of our edges. And for the circuit, it just means it starts and finishes at the same vertex, which we've done over there. So we just started and finished at A. So that example will be both a circuit and a trail. So this would be A, C, B, D, and A. Let's look at the second one. The second one, over here, we can mark in the vertices with their degrees. So this is 2, this is 3, this is 3, this is 2, and this is 2. Now let's have a look at our conditions over here. So for the first one, it has to have exactly 0 or 2 vertices that have odd degree. And you can see that we've got exactly 2 vertices of odd degree. The rest of it is even. And for the circuit, it says has vertices that are all of even degree. This is certainly not true, because you can see that these two are not even. So in this case, we only have the trail, but not the circuit. So the reason why is because there are 2 odd vertices, with the rest being even. And in our case over here, basically we can trace every single edge, but we don't necessarily start and finish at the same point. So an example could be we start from E over here, then we go to A, and then we can go to D, and then we can go to E, and then we can go to B, then we can go to C, and then we can go to D. So we started at E, we traced all the edges like this. So E to D, E to A to D, and then back to E, and then B, and then C, and then D. But we started and finished at the same point, which is why it's not a circuit. So in this case, for part 2, we have E, A, D, E, B, C, D. And in the last one, we'll mark in the vertices. This will be 3, this will be 2, this will be 3, 3, and 3. And you can see in this case we've got 1, 2, 3, 4. We've got 4 vertices that are of odd degree. So if you have a look over here, it certainly doesn't satisfy this condition here, because this one is 0 or 2 that are odd degree. We've got 1, 2, 3, 4. And the last one says has all vertices that are of even degree. This is certainly not the case either. So this one on the right side has neither. So more than 2 odd vertices.